This is an online learning (LMS) project. The task course is EE 301 Communication Systems. Whole material of this course is redacted then dubbed by an American English-speaking TTS, text-to-speech, software, and put into this slideshow with animations for students to easily follow and understand. Instructor, Dr. Ali Kara. Reference book, Communication Systems, Simon Haken, Michael Moher. Random, stochastic, processes, and noise. Random variables. Random processes. Mean, correlation, and covariance. Power spectral density. System responses for random processes. Gaussian process. White noise. Narrowband noise. Random variable, RV. Forming a random variable as the process of assigning a number to the outcomes of an experiment. A function x is a random variable, then its domain is its sample space, and its range is a set of real numbers which are probabilities that are assigned to the elements of the sample space. A random variable might be discrete or continuous. Example, throwing a single die. There are 6 possible outcomes, 1, 2, 3, 4, 5, 6. Assign equal probabilities to each of them so the probability of any one of them is 1/6. Example, a coin is tossed 10 times. The random variable x is the number of tails that are noted. X can only take the values 0, 1, up to 10, so x is a discrete random variable. PDF and CDF. Consider a random variable x for an experiment. The probability of the event, random variable x is smaller than some value x, is denoted as the CDF of x. Capital F sub x of x is the cumulative distribution function. Here are some properties of the CDF. CDF takes values between 0 and 1. It is an increasing function. At -infinity it takes the value 0, and at infinity it takes the value 1. Actually, this minus and plus infinity are the bounds of the sample space, so if the sample space ends somewhere before infinity, then the CDF takes its maximum and minimum values at the corresponding points. Probability density function, PDF, is defined for continuous random variables. Probability mass function, PMF, is for discrete random variables. PDF is equal to the derivative of the CDF. PDF is smaller than or equal to 1. If it is integrated over all the sample space, the result is 1. Question: PDF and CDF. Evaluate the following expressions. P1 equals probability of x is greater than 1 and smaller than 2. X is exponentially distributed with lambda parameter equals 1. P2 equals probability of x is smaller than 1. P3 equals probability of x is greater than 2. Solution for this problem using the cumulative distribution functions is the easiest way. Statistical averages, mean determines the average values of outcomes in a random experiment. For continuous random variables, μx, or E of x, is given as integral from -infinity to +infinity, x times PDF of x, dx. For discrete case, the integral is replaced by summation over the sample space. E denotes statistical expectation operator. μx represents the mean value, the center of gravity of the PDF curve. Question: statistical averages, mean. Find the mean of the exponential distribution by integration, with lambda equals 0.5. Solution: although you can find the mean by taking the reciprocal of lambda, you should solve the integral equation in the formal definition of the expected value. Statistical averages, moments, NDH moment of random variable x is given as integral from -infinity to infinity x to the n times PDF of x dx. First moment is the mean, e, x. Second moment is the mean square value, e, x square. Central moments are moments of difference between a random variable and its mean. It is given by this integral, standard deviation and variance. Second central moment is the variance of the random variable. It is denoted as sigma square x. Standard deviation is the square root of variance, which is sigma x. Variance can be written in terms of the mean. Variance is equal to mean of x square minus square of mean of x. Question: standard deviation and variance. Find the variance of the exponential distribution with lambda equals 0.5. Solution: write the variance through expected values. Then evaluate the first expected value integral by just changing x value to x square. Example: Gaussian PDF. Here is the Gaussian PDF. Note that it is defined for all real values of x. Random, stochastic, process. Random signals are voice signals, television signals, computer data, and electrical noise. Random signals are functions of time and defined on some observation interval. They are random in the sense that before conducting an experiment, it is not possible to describe exactly the waveforms that will be observed. Each sample point in sample space is a function of time. Let us visualize an example stochastic process to understand it better. Following is an ensemble of figures that shows the heat measurement taken from a classroom. Each trial illustrates a measurement day, a total of 365 days, a year, and each figure shows the heat measurement within a day, measured every 1 minute interval. If I want to know about the heat at 12 o'clock noon, I will read the samples taken from each day at 12 o'clock noon, and take their average over 1 year, average or mean value, for a random process x of t. The mean of the process x of t is the expectation of the random process at some time t. Mu x of t is given as integral from -infinity to infinity x times f sub x of t of x dx. F sub x of t of x is the PDF of the process at time t. A random process is stationary to the first order if PDF of x of t does not vary with the time. Say fxt1 of x is equal to fxt2 of x, resulting in mu x of t equal to mu x for all t. Question: average or mean value. Define the random variable y with uniform distribution between 0 and 2 pi. Let x of t equals cosine t plus y for some time interval t 0. Plot x t and t plus x t. Comment on their stationarity. Solution: the two cases, as graphically seen, are not the same in the sense of stationarity. Cosine t plus y is stationary because in time it does not change its distribution. But adding the time variable to x t changes its distribution with time, therefore it is not stationary. In other words, absolute value of cosine t plus y is always smaller than or equal to 1 for all t. Therefore, at any time instant the PDF is the same. However, in the case of t plus cosine t plus y, at different time instances the interval of values that can be taken by this function are not the same. Let's say, when t is 0, this function is in the interval between -1 and 1, but when t is some other value, the interval the function takes values from is changed. Therefore, its PDF is changed, and it is not stationary. Autocorrelation. Autocorrelation is the expectation of two random variables, x of t1 and x of t2. Our x of t1 and t2 is expectation of xt1 times xt2. X of t is the stationary to the second order, or y-sense stationary WSS, if the joint PDF depends only on the difference between the observation times, t1 and t2. Then, autocorrelation function of a stationary random process is given by Rx of t1 minus t2 for all t1 and t2, Autocovariance function of a stationary random process is given by Cx of t1 and t2, expectation of xt1 minus mu x times xt2 minus mu x, which is Rx of t1 minus t2 minus mu square x. Example 5.7. Autocorrelation function of a sinusoidal signal with random phase can be found by employing the methods we just saw. Rx of tau is a square over 2 cosine 2 pi fc tau, where x of t is a times cosine of 2 pi fc t plus theta. Theta is the random phase, which is uniformly distributed over minus pi and pi. Question: autocorrelation. Define the random variable y with uniform distribution between 0 and 2 pi. Let x of t equals 2 pi cosine t plus y for some time interval t 0. Find the correlation of the samples taken from x t at tau equals 1 over 4 seconds apart. Solution: since the process x t is stationary, the only parameter that matters in autocorrelation is the time difference between two sample points. It turned out that samples taken 1 over 4th of the center frequency are uncorrelated. Autocorrelation of a WSS process. Autocorrelation of random process is a measure of randomness. By taking the time difference tau equals t1 minus t2, Rx of tau is equal to expectation of x of t times x of t plus tau. For tau between minus and positive infinity, if Rx of tau changes slowly, then its values taken at t1 and t2 are nearly the same. Slowly varying Rx of tau refers to more low-frequency components. Rapidly varying Rx of tau refers to more high-frequency components. Some properties are: 1. Rx of tau is equal to Rx of minus tau. Symmetrical. 2. Rx of tau is smaller than Rx of 0 for all tau. Maximum value at the origin. 3. Rx of 0 is equal to expectation x square of t average power of the signal, mean square value. For detailed information about the content here, please refer to EE 303, Signals and Systems, and EE 204, Probability and Random Processes courses, which are also prerequisites for this course. Please do so if you are especially having difficulties in understanding these contents, because they are main subject of those courses. Autocorrelation function. This figure shows the idea of a slowly changing and rapidly changing random process. The more flat curve is the curve of a slow process, whereas the curve that is more confined is the rapidly changing process. Example 5.8 Random binary signal. Following is an unsynchronized random binary signal with pulse duration T. It is not synchronized, so that the starting time of first complete pulse in positive time axis is equally likely to be anywhere between 0 and T. This time delay is represented as t. D is a random variable distributed uniformly between 0 and T. When calculating the autocorrelation function of this random binary signal, if we average out the effect of t, we find the following autocorrelation function. Rx of tau is equal to a square times triangular function of t over T, where a is the amplitude of the bipolar binary signal function and T is the signal period. Example: high/low bitrate signals. Here you can see how the previously derived results of different autocorrelation behaviors manifest themselves for the signals with different bitrates. We will see how the bitrate affects the autocorrelation in the next slide. Autocorrelation. See that high bitrate means a concentrated autocorrelation, and low bitrate corresponds to a wider curve for the autocorrelation function. For detailed information about the content here, please refer to EE 303, Signals and Systems, and EE 204, probability and random processes courses, which are also prerequisites for this course. Please do so if you are especially having difficulties in understanding these contents, because they are main subject of those courses. Question: autocorrelation, random binary. Find and plot the autocorrelation functions of two binary streams with bit durations 1 second and 1 millisecond. Cross-correlation functions. Consider two random processes x of t and y of t with autocorrelations rx of tu and ry of tu. Cross-correlation function of x and y is defined as rxy of tu, which is equal to expectation of x of u times y of u. If x of t and y of t are WSS processes, rxy of t and u is equal to rxy of tau, where tau is equal to t minus u. Example 5.9, Quadrature modulation. Consider quadrature modulated processes, x1 of t and x2 of t. Their cross-correlation is -1/2 times rx of tau times sine 2 pi fc tau, where x is the signal in x1 and x2, multiplied by the cosine and sine term. See that for tau equals 0, meaning at some fixed time, the cross-correlation is 0, meaning they are orthogonal to each other. Question: cross-correlation, quadrature modulation in two parts. Part 2, consider a tone quadrature modulation system defined with below signals. x1 t equals cosine 2 pi f m t plus y times cosine 2 pi f c t plus theta. x2 t equals cosine 2 pi f m t plus y times sine 2 pi f c t plus theta. x t equals cosine 2 pi f m t plus y, where y and theta are identically distributed independent uniform random variables. Part 1. Find the cross-correlation function of x1 and x2, and Part 2. Derive the orthogonality condition. Solution. Part 2. After finding the cross-correlation function, we need to find an orthogonality condition between x1 and x2. Orthogonality between two functions means that their cross-correlation is 0, therefore we equate the cross-correlation to 0, and find the solution for tau. It turns out that every half of 1 over carrier frequency delay tau between x1 and x2 makes these signals orthogonal to each other. Power spectral density, PSD. Fourier transform of autocorrelation function is power spectral density, PSD. It is denoted as S, x of f or g, x of f. Some properties for WSS processes are 1. 0 frequency value. Sx of 0 is equal to integral of Rx of tau from minus to plus infinity. 2. Mean square value. Expectation of x square of t is equal to integral of Sx of f from minus to plus infinity. 3. PSD is non-negative for all f values. 4. Even function of frequency. Sx of f is equal to Sx of minus f for real-valued random process. PSD and autocorrelation. Derived from the results we just examined, the PSD of a low bitrate signal is more concentrated, whereas the PSD of a high bitrate signal is more sparse. Example 5.10, sine signal with random phase. PSD of a sine signal with random phase derived from its autocorrelation function is found as 2 direct delta scaled by some scalar value. Example 5.11 random binary signal. Go back to the random binary bipolar signaling case and see that we get the sinc function as the PSD for this signal type. Question: power spectral density, PSD. Find and sketch the power spectral densities of random binary signals with bit durations t1 equals 1 second and t2 equals 1 millisecond. Solution: as expected, because the second signal is varying faster than the first signal, its frequency content is more spread. Example 5.12 Mixing of random process and a sine process. Now consider the case of mixing of random process and a sine process. Y of t is equal to x of t times cosine 2 pi fc t plus phi. Sy of f is found as 1 over 4 sx of f minus fc plus sx of f plus fc. Random process and LTI systems. When a random process is applied to an LTI system, the output will also be a random process. Each sample of the input produces a sample at the output. In terms of PSD, the output of the system can be represented by Sy of f equals Sx of f times magnitude squared h of f. Gaussian random variable. Gaussian PDF is given by fx of x is equal to 1 over sigma x root 2 pi times exponential minus square of x minus mu x over 2 sigma x square, where sigma square x is the variance and mu x is the mean of the random variable x. Normalized Gaussian random variable is the Gaussian random variable whose mean is 0 and variance is 1. It is denoted by the formula 1 over root 2 pi times exponential minus x square over 2. The point of normalizing the Gaussian random variable is that there is a lookup table and some other practical functions associated with it, so the calculations with the normalized Gaussian random variable is somewhat more handy. Here is the curve of the Gaussian random variables. Gaussian random process. Consider random process x of t. Take random variables of the process x of t at x1 is equal to x of t1, x2 is equal to x of t2, and so on up to n, and if the random variables xi of ti for I is equal to 1, 2, 3 to n have Gaussian PDF, then x of t is called Gaussian random process. White noise, AWGN. PSD of white noise is constant over all frequencies, that is, SW of f is equal to N0 over 2 watts per hertz. The factor 2 indicates a two-sided power spectral density. N0 is equal to K times TE in dB per hertz, where TE is the equivalent noise temperature, and K is the Boltzmann constant, which is equal to 1.38 times 10 to the power minus 23. The graph of SW of f is given here. Autocorrelation function of white noise is RW of tau, which is equal to N0 over 2 times direct delta of tau. The average power is found to be infinity. Example 5.14 Ideal LP filtered white noise. Consider passing the white Gaussian noise through a rectangle-shaped filter, whose impulse response is h of f. The resulted signal is Sn of f, which is in rectangular shape, and has an amplitude N0 over 2. Given that h of f has unit amplitude, we know, from what we learned in previous sessions, that inverse Fourier transform of Sn of f yields the autocorrelation function Rn of tau. And remembering that rectangle and sinc functions form a Fourier transform pair, we see that Rn of tau is equal to N0 times b. Sinc of 2b tau, where b is the cutoff frequency of the two-sided response function. Question: LP filtered white noise. Consider passing a white noise process through a low-pass filter. PSD of white noise and filter amplitude response square are given as SW of f equals N0 over 2, and f amplitude square equals rectangle f over 50 kHz. Find the PSD and autocorrelation function of the filtered white noise. Sketch them also. Example 5.15 RC filtered white noise. Now consider passing the white noise through an RC filter. The output spectra of this operation is given as Sn of f, which is equal to N0 over 2. Divided by 1 plus square of 2 pi frc, which is coarsely speaking a quadratic function of order 2. Using Fourier transform, we get the result that Rn of tau is equal to n0 over 4rc times exponential minus absolute value of tau over rc, which is essentially a two-sided exponential function, which we have studied at the beginning of the class. For detailed information about the content here, please refer to EE 206, Circuit Analysis. Please do so if you are especially having difficulties in understanding these contents, because they are main subject of that course. Processing at receiver, Rx. Consider the system denoted here. We are passing an input signal x of t through a bandpass filter and get the output y of t. Now, we examine the operation step by step. White noise, by its nature, is a wideband signal. Transfer function of this bandpass filter is chosen to be of a rectangular shape, centered at some frequency value fc, passing the noise through the filter. We do essentially a scaling, that is, the output function y of f has the same spectra as the filter function, except that the amplitude is scaled by the noise figure, which is n0 over 2. Essentially, we make a wideband input into a narrow band output. Rx processing of white noise, narrow band noise. Steps of processing of white noise are as follows: pre-processing at the receiver, which is called filtering. 1. Bandpass filtering, making the spectra narrow band. 2. Allowing desired signals in the band of interest. 3. Reject all others. 4. Output is narrow band signal. Representation of a filtered noise can be achieved by IQ representation or envelope phase representation. Sn of f is the power spectral density of narrow band noise. N of t is the sample function of narrow band noise. IQ representation, narrow band noise. Take noise signal in IQ form. N of t is equal to n I of t cosine 2 pi fc t minus nq of t sine 2 pi fc t. In phase and quadrature components are low-pass signals. They both have zero mean. If narrow band noise n of t is Gaussian, then n I of t and nq of t are jointly Gaussian. If narrow band noise n of t is stationary, then n I of t and nq of t are jointly stationary. N I of t and nq of t components have the same variance as narrow band noise n of t. See in the figure how the n of t is constructed and then deconstructed into its in-phase and quadrature components. Example 5.17 Ideal BP filtered white noise. As we have seen in previous slides, bandpass filtering a white noise yields the narrow band spectra shown in figure. Here, figure shows single power spectral densities of in-phase and quadrature components of the noise, which are essentially the same. To get the autocorrelation function of n of t, using the IQ representation form, we perform this mathematical operation and find the result to be 2n0 b sinc of 2b tau cosine 2 pi fc tau, and this is how it looks. Question: BP filtered white noise in two parts. Part 1. Consider passing a white noise process through a bandpass filter. PSD of white noise and filter amplitude response square are given as SW of f equals n0 over 2, and HF amplitude square equals rectangle f minus 100 kHz over 50 kHz plus rectangle f plus 100 kHz over 50 kHz. Find the PSD in Part 1 and autocorrelation function of the filtered white noise in Part 2. Sketch both of them. Solution. Part 1. Following the previous slide, it is a straightforward solution. Sn of f equals multiplication of SW of f and amplitude squared h of f. Note that the figure is normalized to n0, as n0 is a parameter dependent on physical conditions and can change from hardware to hardware. Question: BP filtered white noise in two parts. Part 2. Consider passing a white noise process through a bandpass filter. PSD of white noise and filter amplitude response square are given as SW of f equals n0 over 2, and HF amplitude square equals rectangle f minus 100 kHz over 50 kHz plus rectangle f plus 100 kHz over 50 kHz. Find the PSD in Part 1 and autocorrelation function of the filtered white noise in Part 2. Sketch both of them. Solution. Part 2. Now that, do you know the power spectral density of the bandpass filtered white noise? The autocorrelation function can be found by taking the inverse Fourier transform of it. This figure is also normalized to n0. And for better visualization, along with the autocorrelation function drawn in blue, the envelope, which is a sink, is drawn in red. Question. BP filtered white noise. Consider passing a white noise process through a bandpass filter. PSD of white noise and filter amplitude response square are given as SW of f equals n0 over 2, and HF amplitude square equals rectangle f minus 1 MHz over 50 kHz plus rectangle f plus 1 MHz over 50 kHz. Find the PSD and autocorrelation function of the filtered white noise. Sketch them also.